It was rude. I have to expand time.
All right, first off, we have Sana BELLAMINE. She's the Director of Regional and International Infrastructure here at CENIC. She's going to be presenting on CENIC's Spectrum as a Service. And then next we have FADY BEKHIT. He's our Senior Core Engineer at CENIC, and he'll be talking about the MPLS services. And we also have Dennis CAGAMPAN. He's the Manager of our Core Engineering here at CENIC.
Can you hear me? Let's see if this is working. Okay, thank you. Hello, everyone. So the first topic will be CENIC Spectrum as a Service. This is a new offering at CENIC. And the second topic, as David said, will be CENIC's MPLS services. So this part of the presentation is about a new optical solution we will start to offer at CENIC, Spectrum as a Service. And as part of this presentation, I will try to show how CENIC's spectrum provisioning capabilities represent a new asset for CENIC. So for the purpose of this presentation, spectrum applies to spectrum over fiber. We're not going to be covering spectrum as in spectrum for wireless or cellular. So this is only spectrum as it applies to a pair of fiber, just so that it's very clear from the beginning. So the agenda for the presentation, we will start with, from the beginning, what an optical line system is and how services are provisioned over an optical line system. From there, we'll see the difference between a legacy optical line system and then a modern line system or next generation line system that we have been deploying. We'll see, when we talk about a next generation or modern line system, we'll see how a modern line system is an enabler for CENIC's own backbone services as we speak. And we also see how it's also an enabler for new services, and this is when we'll get into Spectrum as a Service. From there, we'll see some very interesting, what I think are two very interesting and unique use cases for Spectrum and Spectrum as a Service, how this new capabilities can facilitate infrastructure sharing, and how it can also facilitate on-ramping a new partner network or a new customer network. And the conclusion will be a quick update about things we're working on the technical side, but also on the business side. So I think we've all seen this map before, but I'd like to go through it very quickly because I'll be referencing some of these locations as we go. So I'll start with Los Angeles. We have fiber going from, so the map, first of all, the map represents CENIC's fiber footprint. And the dots on the map represent locations where CENIC adds and drops services. So there are some locations that are not shown on the map here, and because those are mainly amplification sites, we don't really offer add and drop services at amplification sites. So going through the fiber paths here, starting with Los Angeles, we have fiber going to Tustin, San Diego, to Riverside. We internally refer to this path as a CENIC Southern route. From there, we have fiber going inland into Bakersfield, Fresno, Merced, Sacramento to Emeryville. We refer internally to this fiber as the inland route or the inland path. And then the next long path from Emeryville going to the Bay Area, San Francisco, Sunnyvale, back to Soledad, San Luis Obispo, back to LA. We refer to this path as a coastal path. We have two very important rings attached to the backbone paths that I described. The first ring is from San Diego, El Centro, Yuma, Palm Desert, and Riverside. And then on the opposite side, we have the ring going from Sacramento, Chico, Palo Cedro, Corning, Colusa, and back to Sacramento. So these two rings cover areas that are underserved. And it is great that at CENIC we can actually offer 100 gig plus capabilities at these two locations. Okay. So we'll start from the beginning. So what an optical line system is. An optical line system really has two components. The first component is fiber between two locations. When we first get the fiber, there's no equipment connected to it, and it's typically referred to as dark fiber. There's really no light through it, so therefore it's dark. And then the other component of an optical line system is the optical equipment that terminates the fiber at each end. And in general, that optical equipment at each end provides two functions. The first function is it allows us to multiplex multiple services onto one fiber pair. And the second function is it allows us to amplify the signal so that we can carry multiple services from one location to another location. So in this diagram shown here, the fiber that's shown is between two CENIC hub sites in Los Angeles and Tustin. But the same setup, we have the same setup between CENIC hub site and a CENIC associate, or between two CENIC associates. So we saw what an optical line system is at a high level. So now we'll go into what a service over an optical line system is. So what is a service to start with over an optical line system? Typically, when we get requests for a service over our optical line system at CENIC, the purpose of that service is to carry IP traffic. So I'll start from here, and that service could be 100 gig service, 200 gig service, 400 gig service. So we'll just keep it simple, assume the service is a 100 gig service. So this is our router port, which is a 100 gig port. From there, we have a connection into a piece of equipment. Maybe I should move here. A piece of equipment called a transponder. The function of this transponder is really to take the payload as received from the router and transport it into a unique color or unique frequency into the line system. From there, go to the other side, and then where we have a matching transponder at the opposite end, and then that transponder delivers the payload back to the router port at the opposite side. So this is how typically we provision like a 100 gig service for our associate or even for our own services. The payload is mapped to a unique frequency or unique color that's carried over the fiber. This is just a continuation of what we just saw, just to illustrate how it is possible to provision multiple services over the same fiber. In this case, we're provisioning 3 by 100 gig services. So we're using 3 colors or 3 frequencies that are all carried over that same dark fiber and then delivered on the opposite side to the router port at the other end. Just making it a little bit, adding a little bit more complexity to it. So in the examples we saw so far, these 100 gig services or 200 gig services we provision were between adjacent locations. We may need to provision services that are not between adjacent locations, and when that's the case, we need to express those colors through some intermediate locations, such as shown here. In this example, we're provisioning services between Los Angeles and San Diego, so we need to express those colors through locations Tustin and Oceanside. Okay, so now that was kind of some background information before we get into like the concept of spectrum. There are 2 types of optical line systems. There's what's like legacy optical line system, and there are like modern line system or next generation line systems. And the 2 line systems have many, many differences, and we're not going to get into all of them. For the purpose of the discussion, I will focus on a limitation in a legacy line system, which is that it is a fixed grid line system, and compare that to a capability in a modern line system, which is it has flexible grid capabilities. So those are really the 2 things we'll focus on most when we compare the 2 line system, and that is the most important difference in my opinion. So in this example, we'll see how service is provisioned in a legacy line system. So we still have the same topology we saw earlier. We have fiber between 2 locations, and we have the terminating equipment at each location, the optical equipment at this location. In this case, we have a legacy line system, and it has that fixed grid capability limitation. What that means is any time we provision a service, we're going to consume 50 gigahertz of spectrum. So whether that service is 10 gig or 40 gig or 100 gig or 200 gig, anytime a new service is turned up, we're consuming 50 gigahertz of spectrum. The other issue with the legacy line systems in general, we cannot provision more than 200 gig of capacity in one service. So we're really limited to transponders that deliver 200 gigabit of capacity per service. One thing I should have mentioned a little bit earlier, so most providers, when they operate a line system, they operate in what's called the C-band. In the C-band, the amount of spectrum that's available to us via this fiber is 4,800 gigahertz. And this is how we're operating at CENIC as well. We're still operating just in the C-band. So before I leave the slide, just a quick reminder that one of the main limitation of this legacy type of line system is that every time we provision a service, we're consuming that 50 gigahertz of spectral capacity. Now, the slide covers how a service can be, what the options are when the service is a modern line system or a next generation line system. So we still have the same topology, the fiber between the two locations. We're still operating in the C-band, so we still have that 4,800 gigahertz capacity available over that fiber. The difference here is that the terminating equipment at each end is next generation equipment that's modern optical equipment that has flexible grid capabilities. So the key point in this type of line system is the amount of spectrum that's allocated to a service is the amount that the service actually needs. So we're not really restricted by that 50 gigahertz of spectrum. The service gets the amount of spectrum it requires. The other important benefit of this type of line system, it supports next generation transponders. So these are transponders that can deliver very high capacity, 400 gig, 500 gig, 800 gig, and even 1.2 terabit. They use very advanced modulation or encoding techniques so that the amount of spectrum that's used by these transponders is really optimal. For example, there are so many options today for next generation transponders from different vendors that can deliver 400 gigabit of capacity within just 75 gigahertz of spectrum. There are many options for transponders from different vendors that can deliver 800 gig of capacity with just 125 gigahertz of spectrum. So I hope you're starting to see how powerful these next generation line systems are. With that, I mean, in this type of line system, same thing as a legacy system, we can provision multiple services over the same fiber, and we're still in the C-band, still limited to that 48 gigahertz of capacity. So now, the purpose of this slide is to show how we at CENIC are starting to benefit directly from this new infrastructure. We've already upgraded the southern path to FlexGrid, and we've already upgraded the coastal path to FlexGrid. We're working on the inland path, so that work is ongoing. So because we've already upgraded the southern path to flexible grid and the coastal path to flexible grid, we're in the process of migrating from the legacy way of provisioning services to this new way of provisioning services that uses next generation transponders and leverages the flexible grid capabilities we have. So the top part, and I'll be referring this diagram a couple of times as we go along, the top part of the diagram is a legacy way of provisioning services, and the bottom part of the diagram is how that same capacity can be provisioned in our modern line system. So in the top part of the diagram, as an example, today between Los Angeles and Tustin, CENIC has 300 gig of capacity to carry CENIC's IP backbone traffic. That service, there's two, in a legacy, if that service is provisioned in a legacy way, the way at least it was for a long time until we upgraded the line system, we have 3 transponders, 1 transponder per 100 gig as shown on the far left, and the 3 transponders on the right. Because we have 3 services and because it's a legacy line system, each service consumes 50 gigahertz and each service carries 100 gig of capacity. So in the top part of the diagram, we're consuming 150 gigahertz, 3 times 50 gigahertz, 150 to carry 300 gig of capacity. In the bottom part of the diagram, we're actually in the process of making all these migrations. We're provisioning that same capacity using a next generation transponder, and we are only using 75 gigahertz of spectrum to deliver the same amount of capacity. So So I just wanted to have on the same slide like the comparison between the old way of doing things and how the new way of doing things. So as we go from like the top way of delivering provisioning, the legacy way, to the new way of provisioning things, we're significantly reducing CapEx. I mean, as we saw in the top part of the diagram, each 100 gig service requires its own transponders. And there are variations to that, but that's really the most common case. And the additional use cases we're working on for the CENIC backbone are all these use cases. And when we're done with this work, we will see a minimum savings of $800,000, and that's really a minimum. And all this like reduction in the backbone budget can be carried over to CENIC Associates in the future. In addition, as we migrate from the legacy provisioning method to the new provisioning method, we're also seeing significant amounts of savings in OpEx, space and power. As an example, the transponder I showed at the top in the previous slide consumes about 2 amps. We had 3 on the left, 3 on the right. That's 12 amps. The one at the bottom consumes a maximum of 7 amps. So for both units. So CapEx, OpEx as well. We're seeing significant savings there. I'd like to spend a little of time on this end-of-life point here. So the transponders, 100 gig or the transponders we bought at CENIC, we bought those 5-6 years ago, and they're slowly starting to get into an end-of-life cycle. So the time is coming where we need to replace the transponders, do a transponder refresh. But by taking this approach where instead of doing a one-to-one replacement of the transponders, we're enabling flex grid capabilities on a line system and immediately going to next generation transponders for the same services, we're eliminating this need for the one-to-one replacement of equipment. So this is really another great benefit from these migrations we've been doing. The last point is, as we do these migrations, we're obviously, those 100 gig transponders become available and they can be useful for specific projects. So we'll have a pool of those as well for specific projects. So the purpose of this slide now is to show how this capability is really representing is becoming an asset for CENIC. So I'd like to start here. So in the example I showed earlier, in the top part of the diagram, we were using 150 gigahertz. When we did our migration, we only used 75 gigahertz of spectrum. So now we have 75 gigahertz of spectrum available to us on the fiber. And that 75 gigahertz of spectrum becomes a business opportunity or partnership opportunity. It is extra, it's available on the fiber, and it can be used for a new project, for partnership, for a new product. So it becomes an opportunity for CENIC. So if we at CENIC continue to be very efficient with the amount of spectrum we use for our own services and for services needs by our associates, the end result is that we will have some amount of spectrum available that can be used to offer spectrum as a service. So this is like a new product, and we've already turned up a first set of connections slowly. But as we continue to migrate our backbone services to the next generation way of provisioning services, we will have spectrum capacity for offering the spectrum as a service. So, and this can be offered, the spectrum as a service can be offered in 2 options. The first option is we, CENIC, recommend the next generation transponder we use based on our experience and based on we've tested and validated. So that would be the first option. The second option is to bring your own transponders. So our customer or associate can bring their own transponders, work with the CENIC engineering team for validation, because some amount of validation needs to be needed. And from there, they can use their own transponder over the spectrum amount they acquire from CENIC. So this is an example. This is done. I'm just going to talk about it. So this was all done. This is one of the great use cases of spectrum and spectrum as a service. And this is a project we worked on with Aranet 2 last year. So up until last year, Internet 2, they had their, we CENIC, obviously, we have our own line system between Los Angeles and Sunnyvale. Internet 2, they had their own line system between Los Angeles and Sunnyvale. Very similar path, fiber paths, very similar locations. CENIC being like the R&E for California, we're using about 1,500 gigahertz of spectrum out of that 4,800 gigahertz. So we're using quite a bit, but there was capacity still available. Internet 2 doesn't have that many services between Los Angeles and Sunnyvale. Most of the services that Internet 2 had at that time was like for Pacific Waves, the Pacific Wave Exchange backbone services. So their line system was, they had plenty of capacity between Los Angeles and Sunnyvale. So from there, we worked with the Internet 2 team, and it really meant there was room for consolidation here. So we worked on a project last year, and where all of Internet 2 services now between Los Angeles and Sunnyvale are carried over the CENIC optical line system using a spectrum service. So Internet 2 is carrying about 1 terabit of capacity between Los Angeles and Sunnyvale, and they're within 250 gigahertz of spectrum. In addition to that, Pacific Waves backbone between Los Angeles and Sunnyvale is over CENIC's line system. Pacific Wave has 500 gigabit of capacity over 125 gigahertz of spectrum. The Pacific Wave migration was made possible by National Science Foundation. The next generation transponders used for migrating Pacific Wave services to spectrum was funded by the NSF. So this is another, I think, great use case of spectrum and how spectrum as a service can be very valuable. So in this example, and this is a bit of a hypothetical example, even though we're starting to run into some use cases already, the service provider have services between Bakersfield and Fresno. They have infrastructure and fiber between the two locations. But this service provider would like to extend services to Sacramento, but they don't have fiber between Fresno and Sacramento. Fiber builds take a very long time, months to up to years at times. So CENIC has an optical line system between Fresno and Sacramento. So what this service provider can do is they can buy like 75 gigahertz of spectrum from CENIC, identify the transponder that allow them to achieve a minimum of 400 gigabit per second over that 75 gigahertz from spectrum. And from there, they can immediately extend their services to Sacramento. They don't have to wait for the fiber build to complete. And then when the fiber build is complete, at that point, they can migrate their services to their own fiber. So we're starting to see some of these use cases as well. So this is my last slide. So things we're working on. So the cost model for the service has to take into consideration the following: the cost of the optical equipment, the cost of the maintenance for the equipment, the cost of the fiber, the cost of the maintenance for the fiber, the maximum amount of spectrum that's available of that fiber. So if it's just a C-band, it's 4,800 gigahertz. What's the fraction of that the customer would like to get? In addition, we need to take into consideration the fiber distance traversed by the service. So I showed in one of the examples where if the service is needed between two locations that are not adjacent, we will need to express the service via some intermediate location. So therefore, we will be consuming spectrum over those intermediate locations, even though we're not necessarily dropping the service at those locations. So if the distance is more than 2 hops, then we need to account for the amount of spectrum uses over the intermediate locations. So those are the things the factors that will drive the cost, that are driving the cost model. Of course, there's engineering time, but I'm not going to put that in here. So on the technical side, we continue to enhance our monitoring capabilities and validation capabilities for these next generation transponders, because at the end, they're not really native to the line system. They're alien to the line system. In addition to that, we're starting to think about spectrum as a service phase 2, where it's a large amount of spectrum, 400 gig, we can offer like 400 gigahertz, 500 gigahertz, and see if the customer can provision more than one service over that amount of spectrum, 2 services, 3 services, so really have more freedom to do what they want within that large amount of spectrum. And this is this is a project we'll be working on in partnership with our line system vendor. So thank you. From that, I think I'll turn it over to FADY and Dennis for the MPLS section.
Thank you, Sana. So now we're going to talk about a few layers higher than the optical line system. So we'll be talking about MPLS-based services within CENIC. So what we're going to talk about is CENIC's journey to providing MPLS-based services, starting with why we did have to consider that, what it is, and how we implemented it, and a summary of the project milestones and the outcomes. So starting with why did we move to MPLS? So other than the Caller and DC service, Ethernet Layer 2 services has been the most popular service that CENIC has been providing. And the only way to do that prior to our MPLS implementation is to use hop-by-hop cross-connects or hop-by-hop native bridging. And as you may think, why did we do that is because the lack of being able to tunnel that across the network. So services provisioned in a hop-by-hop manner is not resilient to failure. So what that means is that if for some reason the way that Layer 2 service has been provisioned, the path for it went down, it will not find another path on its own. It's also complex to operate because if there's 5 hops to provision from A to Z, then there's 5 devices and 5 times the work in order to do that. And also 5 times the documentation, 5 times everything. And the way that we are already doing that complex configuration, it is only valuable for Layer 2 services. If there are other services that the community needs, we have to find another way in order to implement it. So we had to think of like, what can we do in order to deliver this service better and at the same time be able to support the community better as well. So we went with segment routing MPLS, and one of the main advantages that it has for us to choose it was that improved resiliency. So it's not anymore done in a hop-by-hop method, so the path between the 2 locations are now signaled dynamically, which means it now adapts to failure. So if there's a failure along the path, it will now signal again in order to find another path that is working. Another thing is that segment routing MPLS allows us to have a faster time to recovery because of its inherent nature of being able to pre-install backup paths. Another thing is simplified operation. So since we are just configuring 2 ends of the service, it's simpler for us, quicker for us to deploy it, and at the same time, since it's simpler to operate, there would be less mistakes, and the community would benefit from that because there would be less accidents in their services. And then next is that segment routing MPLS builds the foundation for CENIC to be future ready. So since we are not natively bridging or doing hop-by-hop cross-connects, and now we're using labels to tunnel everything, it's now going to be significantly scalable. It will support all of the current services that we have on our service catalog, at the same time be ready for future type of services that the community may want or may need. And another thing that it builds up is that segment routing MPLS allows us to handle different traffic patterns in the future if we need it through flexible algorithms and segment routing traffic engineering. So for the details of our journey, I'll pass it over to FADY.
Thanks, Sana. Thanks, Dennis. In the next 15 minutes, I think, I'm going to discuss about the MPLS from the technical perspective. And as Dennis mentioned, MPLS has a lot of values for CENIC and our associates and members. And let me first start to explain or to give introduction about MPLS and like at the beginning ask what is MPLS. So MPLS stands for multi-protocol label switching, and it's a routing technique that direct data from one node to the next based on labels rather than network addresses. So for example, as you see here in this slide, once the packet is received by the MPLS-enabled router Los Angeles, a new label has been added to the packet or pushed to the packet. This label is going to be used by the next router, which is Tustin, to be forwarded to the next router, which is Riverside. And this Riverside router will send it to its destination without the label. So that is the first thing that I wanted to mention, is that it's not depending anymore on the IP addresses. It does not depend on the IP routing. It depends on the label that's assigned or pushed to the packet. But these labels that you can see here in these diagrams that's being pushed to the packet is actually identify an established path between one node to the other. For example, the node between Los Angeles, Tustin, and Riverside is identified by these labels that you can see here. That's why we call it an established path or between endpoints. This established path is what we call tunnels. So MPLS actually create tunnels automatically between the labels. So we will have a tunnel which is identified by these labels between Los Angeles and Riverside. The same thing will be repeated between Los Angeles and Riverside, between San Diego and Riverside, and between all of the other nodes. That will be done automatically. So that's why these tunnels, which is created between the endpoint, is a key point in the MPLS, and that's why we consider the MPLS as a tunneling technology. MPLS is used in most of the service providers right now, even though they are using other technologies, but MPLS is a must and can be used and must be used in all of the backbone of the service providers that we have right now. So the next question will be, how did we create these labels? How we identify this label, or by another meaning, how we create these tunnels. So at the initial implementation of the MPLS, these labels has been identified manually. So you can go to the router and configure it with the specific label to identify it, similar to what they usually do with the ATM and frame relay, old technologies. But later on, they started to have a dedicated signaling protocols that is managed to be responsible for assigning this label or creating these tunnels, like LDP and RSVP-TE. But back in 2013, there is a new technique that's used to create this or assign this label, which is the segment routing. And CENIC actually is using that advanced technology, the segment routing, to assign these labels and create the tunnels. So the segment routing concept depends on the source routing concept, and it's not something new. It has been in the technology for a long time, used in other implementation and used in IPv6 and other technologies. The source routing concept depends on, or meaning that only the edge routers or the endpoints will be responsible for assigning these labels. Meaning that, for example, if Riverside router, as you can see here, has specific node IDs, unique and configured for it, like 16,008, the Los Angeles router, which is the first endpoint or the first edge, is going to use this 16,008 label to forward it to Tustin. And this label is identifying the path. So the segment routing is depending on the source routing concept, and it might add several labels. However, it will identify the path between Los Angeles and Riverside. Tustin will not contribute in this assignment for the labels. There will not be any additional signaling protocol that is used to assign this label. However, the endpoints are only responsible for that. So, as I will explain later, this tunnel is going to carry our important traffic. All of our members and associates traffic will be using this tunnel to move from Los Angeles to Riverside. Being said, we must think about a way to protect this tunnel. And what we are using in CENIC is a technology called TI-LFA. TLFA stands for Topology Independent Loop-Free Alternative. And it actually protects the tunnels against any failures that can happen in the main tunnel. And basically it worked by creating or pre-installing a tunnel as mentioned, as Dennis mentioned, pre-installing another tunnel, which is that gray tunnel that you can see. Once the main tunnel is created, another tunnel will be pre-installed, which is that gray tunnel that you see here. And once there is a problem in the main path or in the main tunnel, there will be another, the traffic will be using the other protection tunnel immediately. Or we can say that within theoretically a 50 millisecond convergence time without waiting for any other convergence for the IGP or whatever. And TLFA is not the only technology who can do that. There is another technologies that can protect the tunnels as well, like fast reroute or even the regular loop-free alternative. But the TLFA that CENIC is using is capable of providing 100% protection against any problem in the network, regardless the topology looks like. Whatever the topology looks like, whatever the main tunnel is created, there will be another protection tunnel that's pre-installed and will be used once there is a problem happen in the network. And this is a key point here for the TLFA that CENIC is using. So now we have our MPLS. We have our MPLS ready for in the network. It's enabled with segment routing, TLFA, and EVPN and other stuff I didn't also mention here. So how does CENIC offer these MPLS-based services to our associates and members? Yeah, we have our backbone ready, but I didn't talk about how we are going to offer this for our members and associates. So let me explain first what is happening right now. So what you see in the first block here, the legacy or no MPLS, is the solution that is happening right now, and this is actually what we want to move away, what we want to migrate from. So what happened is that we stitch the VLANs across CENIC backbone using local cross-connect configuration, meaning that, for example, if one of the UCs want to have a connection to, or one of the UC VLANs, if we would like to be more accurate, want to connect to Internet 2, we would have to create a local cross-connect that connect one of the interfaces of Riverside to the other interfaces, that green connections that you can see on the first block. And we have to do the same also on Tustin. We have to do the same at Lex, all the way until we reach Internet 2. Of course, you can see that it is a static manual configuration that has been done across the backbone. After we enable the MPLS, we have the MPLS-based services. We enable the backbone, as I explained before, with the segment routing, TLFA, and EVPN. So now we can offer E-lines and E-LAN services to our associates. So with the same application, what we can create is that we can have an E-line, a direct L2 VPN that is dedicated for the connection of this VLAN for this UC to the Internet 2. This is what we call E-line, and this is one of the 80% of the services right now that's provided by the EVPN is using the E-lines, which is a point-to-point. Similarly, we have also the E-LANs, which is exactly the same, but if we would like to have multi-point to multi-point. What I want to highlight here is, as you can see, the configuration is done only on Lex and Riverside. We don't look about what's happening in between. It is something that is a function of the MPLS. This is the tunnel's work. We don't have to think a lot about what's happening in between. And this is the key point here in using E-lines and E-LANs. Having the E-lines and E-LANs is already, you can see it on the network service catalogs that CENIC has, and I put here the link. I think anyone can access CENIC website and can check the E-lines and E-LANs, and depending on what solution you would like to have, of course, after communicating with the PMO team, you can get whatever you would like, depending on what's the solutions that you would like to have. Yeah, so what is the difference between the network or the services before MPLS and after MPLS? So before MPLS, And I will be discussing that in the form of that example, that visual example. I will be discussing related to these examples with respect to the configuration and with respect to the reliability. So before MPLS, the local cross-connect has to be configured at each router, as I explained before. And that is really similar to that example, that traffic example. So we have like that traffic roads, or that's example that's representing scenic network or scenic backbone. We have this roundabout which is representing the routers. We have this car which is representing a layer 2 frame. And if we would like to guide this car to go from one node or from the source to the destination, there must be a traffic engineer who has to put these signs that you can see at each roundabout to manually guide this car to go from one roundabout to the next one and so on. So for example, the first one will put a sign mentioning, hey, you have to take the third exit. And he has to put another sign as well in the second one to take the first exit and so on. So what you can see here is that it's a very hard operation. It's static. If any mistake happen, the car will not reach its destination. And this is exactly similar to the configurations that we are currently doing right now in the before MPLS. In the same example, okay, but if we were discussing about the reliability, traffic is interrupted in case of node or link failure, although the availability of the other path. So as you can see here, there's a roadblock happen at one of the roads along the path of this car. So this car will be blocked. It cannot reach its destination, although the availability of the alternate path. Okay? And if you would like to create an alternate path, you have to double the configuration to create another path to go to that other one. And you have to do this switching manually as well. So that's exactly what's happening in before MPLS, that some of the traffic has been lost because of the manual configurations that we have in our network. However, after MPLS, the situation is changed. After MPLS, we have MPLS segment routing will automatically create the main and protection tunnels. It's exactly similar to having a smart traffic map where a blue line, this blue line or blue lanes is painted on the road, which represent a lane for that car to go from this source to the destination. And what you will need to do is on the edge routers only, that traffic regulator guy will say, hey, you can follow the blue instructions, which is exactly similar to the main tunnel that we have, okay? And that is the only thing that we have to configure here, like edge routers configuration only. And in case we have a problem in this blue lane or blue line, so in case of node failures, traffic will be directed to the protection tunnel automatically. Okay, and this is exactly similar to what we have. There is a roadblock, and then the traffic regulator will ask the car to follow the red path or the red lane, which is already pre-installed and pre-painted to protect the main tunnel. Automatically, that will happen automatically. So again, the key point here is that that configuration will be on the edge routers only, without having to take care a lot about what's happening in between. Last slide is about the milestones. So to reach this position, there has been a lot of efforts done. Like since 2020, team has done a lot of proof of concept to prove the concept of MPLS and E-lines and ELAN. And then back to June 2011, I think, 2021, we have done a lot of trainings for our internal staff and employees, external and internal, and then we standardized the configuration of Cisco and Juniper in our GitLab. And then we pushed the configuration to our backbone routers, and to complete the picture, we enabled the EVPN as control plan, and we added the services in the service catalog. And then we tested these services first on our internal services, systems services. And finally, starting February 2022, we started to migrate, we almost close to 50% migration of the legacy MPLS services to E-lines and ELANs. So it's a very long journey that we started. Let me summarize what we say. So I explained at the beginning what is MPLS. It's a tunneling technology. We have been using advanced MPLS technologies in our implementation, like segment routing, TILFA. We have enabled MPLS-based services like E-lines and E-lands as an L2 VPNs, and the new services enhance the resiliency and facilitate the deployment and troubleshooting. I think that is all. Yeah, thank you. So now, do we have some minutes for questions?
A question about Spectrum as a service. Who is your target customer?
Everyone. All right. So we actually have a set of customers that have N by 100 gig services. So I think this would be our first target, where if they can purchase like these newer transponders and provision like a 300 gig, 400 gig optical channel, then we'll be able to gain some spectrum capacity back.
What I mean by is what type of organization or company or institution might be your customer? What type?
Yeah, so as an example, many CENIC associates. So first ones that come to mind, I'm only going to say the UCs for now, because typically the UCs got their first 100 gig services. We're starting to see a trend where some of the UCs are migrating to 2 by 100, and we're even seeing the very first UCs asking for like 400 gig service. So they can be a target customer as well. So really it's two sets of customers who want to go beyond 200 gig, and second target can be existing customers that already have N by 100, where we can be more efficient in general by provisioning just one spectrum service instead of like multiple wavelengths. Yep.
Yeah, another optical question on the shared spectrum. So are the customers actually managing their own transponders, or are you managing them on behalf of the customers?
So we do a lot of validation. And when that validation is complete, then they manage their own transponders.
Okay, and so I guess follow up to that then is, how are you dealing with like gain control issues and protecting your optical network from customer configuration mistakes or customer configuration like just, shutting off the lasers and causing gain recalcs and stuff like that?
So we require a specific launch power. For example, is one of the things we require. This service is tied to a specific central frequency. So there's a lot of requirements we still have in place to make sure it's, at least during this phase one, it's controlled.
All right, cool. Thank you.
Yep.
And one question on the MPLS side. Are you using MPLS like for next hops on your IP internet transit service, or are you still using IP next hops for like, just regular internet transit services?
So as part of that journey as well, we did a transition to like making sure that all of our edge, our redistribution from our eBGP to iBGP is now a next hop self. So because of that, the next hop is now always the loopback of our routers, and that allows the node SIDs to always label switch everything, including global IP table.
So you are label switching your IP table then?
Yes.
Okay.
So on our platforms that have already been transitioned, yes.
Very cool. Thank you.
All right, first, great presentation. Really appreciated it. What is your vendor and platforms for both your optical system and your packet platform?
Vendor and platform?
Yeah.
Okay. Our line system is an NCS2K line system from Cisco, and in terms of transponders, we've already we have used for alien services, like using Spectrum Sienna gear. We've also used for some customers Eptronics, I think that's what the name is. So those are and of course Cisco. Yeah.
And what's your packet platform?
Oh, I'm sorry?
What's your packet platform?
Okay. All right.
So for the packet, it's going to be a mix of Cisco NCS-based. We still have some Cisco ASRs, and then we have Juniper MXs. So, but at the end of the day, at least from a segment routing platform, we're normalizing into Junos platforms and iOS XR platforms.
All right, let's give them a round of applause.